Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett and we cover all things Gen Chem related on this channel. On this video, we're going to be covering redox reactions and we're going to learn all about them and how to predict them. Let's get started. So in previous videos, we discussed different types of reactions. We learned about precipitation reactions, acid-base reactions, and some gas-evolving reactions that can occur. And this typically happens when we're exchanging ions in solutions. But there are also other reactions that involve transferring electrons to one atom from another, and these are known as oxidation and reduction reactions, or simply known as redox reactions. And so when we have these redox reactions occurring, typically what we're doing is we're converting an atom or some type of elemental form of an element into an ion, and it's that transfer of electrons that we're going to want to track. And so a lot of times these redox reactions may involve oxygen, but we're going to learn that they don't always have to. So an example of a redox reaction is shown for you here, where we have solid iron reacting with oxygen, and then we're creating this ionic compound, this iron 3 oxide, that now has these ionic species that are embedded within this molecule. And so how did that happen? Well, in redox reactions, one of your elements is gaining electrons and one of them is losing them in this transfer process. And so combustion, we learned about combustion before. Combustion is an example of a redox reaction, where if we took something like hydrogen gas and oxygen gas and reacted the two, what we create is something like H2O. Again, we have this transfer of electrons to create this new substance. We can also have redox occur, or this reduction and oxidation process occur, without oxygen being present. So for example, if we have sodium and chlorine reacting with one another, sodium, solid material, and the gas chlorine, these combine to form sodium chloride. And so we're losing electrons and gaining electrons to create this ionic material. And so during this process, electrons are transferred from sodium to chlorine to create this sodium chloride material. And so we would say that sodium is considered to be oxidized because it's lost some electrons, and chlorine is being reduced because it's gained electrons. And so you can see these kind of half reactions shown here, where sodium is just giving up its electrons to allow chlorine to become this negative species. And now once those positive and negatives are created, they can attract to one another and something new is being formed. So when we have these reactions that are occurring between metals and nonmetals, that they're typically characteristic in some of these redox reactions, something you should notice is that in each of these scenarios, we have these pure elements that are being converted to ions. And in each of these cases, we're either losing electrons, like the metal, or we're gaining electrons, like the nonmetal. And it's that gain and loss that creates these ions and allows them to be attracted to one another. And so what we're going to be doing is determining who in the reaction is being oxidized or reduced. And that's based on, have I lost an electron or have I gained an electron? And so the redox reactions are going to be converting free elements into ions by either gaining or losing electrons. Remember, if you have somebody that's losing some electrons, somebody has to be available to take them and gain them. Okay, so how can we remember this? I like the saying, Leo the lion says grr. So Leo stands for loss of electrons, means that you are oxidized. Okay, so if I'm losing electrons or if I'm becoming more positive, I'm being oxidized. And GR stands for gain of electrons, means that I'm reduced. I know some other teachers use oil rig, so oxidation is loss and reduction is gain, but I'm a Leo, so I like Leo the lion says girl a lot better. And it's just a little easier to, roll off the tongue. Loss of electrons, you're oxidized. Gain of electrons means you're reduced. And so in this example here with the sodium and chlorine, well, our sodium went from having no charge to now having a positive 1. So that means it lost some electrons. So sodium is being oxidized. And chlorine went from having no charge at all, and then it gained some electrons, so it took on a negative charge. So it gained electrons, which means it's reduced. And so they come in pairs. If something's being oxidized in a reaction, something is being reduced. Okay. All right, so how do we track this? Well, the way that we go about tracking these numbers, these charges that are seemingly present, is through this electron bookkeeping system. And so a lot of these reactions may not involve oxygen. So we need to come up with a way to track where these electrons are going and assign a value to each of the elements that are found in these reactions. Now, that assigned value is what we call an oxidation state or an oxidation charge. And that allows us to track. Now, be wary or be cautious that just because they look like charges, they are not ion charges. In fact, they're just really an imaginary charge that's assigned based on some rules that we're going to see to help us actually track where the electrons go. And so remember, ions are real charges, they're measurable, but these oxidation charges that we're going to look, although they look really similar to charges, they're different. So put a star on these next few slides because this is going to give us the order for how we're going to go about assigning these oxidation states or charges, okay? And so they're in order of priority. So as you're dealing with a compound and identifying and assigning these oxidation states, you got to go think about these in order of priority. So a free element, so an element that's by itself, will have an oxidation state of 0, okay? So it hasn't gained or lost any electrons, so we just say it has a 0 oxidation state. So like sodium by itself, chlorine by itself would be 0. All right, rule number 2, monatomic ions have an oxidation state equal to their charge. So monatomic means singular charge, +1 charge, have an oxidation state equal to their charge. So group 1, group 7 would be +1, -1, as they've been before. Rule 3, the sum of the oxidation states of all the atoms in the compound will equal up to 0. And so if I say, you have certain number of positive cations and certain number of negative anions, the overall charges have to add up to 0. And so that'll help you out when you're trying to assign some oxidation states that may not fall within some of these rules. All right, continuing on. The sum of the oxidation states of all the atoms that are found in a polyatomic ion will equal the charge of a polyatomic ion. So for instance, if we have something like nitrate, we could say that oxygen would be -2, and that's going to be based off a rule we're going to see in a little bit. Now, we could not say that it's going to be the same we couldn't say nitrogen would be -3 like we would predict off of the valence numbers. And that's because it would not add up to -1. And so we can use algebra to help us to predict what that nitrogen would be. If we don't know the charge in that polyatomic ion, we could say, well, I don't know what nitrogen is, but I do know that oxygen is -2, and there's 3 of them. So therefore, my nitrogen must be +5. Okay, so we'll go through some examples. Rule number 4, group 1 metals have an oxidation state of +1. So that coincides with the monatomic rule that you would expect a +1 for group 1 metals. Group 2 metals also have an oxidation state similar to their charge, so +2. So that makes it easy. And then the last rule is that when compounds contain some of these nonmetals, the oxidation states will be according to this table. And so again, a lot of these you've seen before. So you have fluorine would be -1, hydrogen would be +1, oxygen -2, group 7, -1, group 6, -2, and group 5, -3. And again, these are in priority. So based on if you have like oxygen and nitrogen together, oxygen takes priority. And so that means that nitrogen has to shift, okay, as we saw in that previous example. Okay, so let's practice assigning oxidation states to the following. So bromine by itself would be how many? What charge? Would be 0. Potassium is a monatomic charge or group 1 element, so it would be +1. So for LiF, lithium fluoride, when we're looking at this, we know overall the charges have to add up to 0. I know potassium is a +1, it's group 1. Fluorine is -1, group 7, and that all coincides with the rules that we've seen. All right, carbon dioxide. Now, what would the rules here be? Well, this rule, the precedence is going to go to the fact that the sum has to add up to 0. We know that oxygen would be -2. And therefore, carbon would have to be +4 to balance this out. Now sulfate, in sulfate, we know the rule that takes precedence is that they have to add up, the charges have to add up to the oxidation states have to add up to the charge of this polyatomic ion. So they have to add up to -2. And so out of the oxygen and sulfur, the element that takes precedent is oxygen, would be -2. And so we don't know what sulfur would be. Sulfur is also in group 6, but if we made it -2 as well, then it would not add up when we add everything up to -2. So sulfur has to take on a different charge. So we would say unknown plus -2 times 4. And when we solve that out, our unknown sulfur would end up being +6. Okay. And then Na2O2, this is a little tricky one. So remember, the rule here is that overall, these have to add up to 0. Now, the thing that takes precedent in this example is actually sodium. Sodium is group 1, it's monatomic. And so if sodium is +1 in this case, that means that oxygen in this case must be -1, not -2, to balance this out. That's the only way that we would end up with all of this equaling up to 0. Okay, so just pay attention to the prioritization of those rules. So another way we can look at things is we can actually predict in a chemical reaction what element is being oxidized and what element is being reduced based on how these oxidation states change throughout the reaction. And so what we would have to do is first assign all the oxidation states for each element that's found, and then we look for who's gaining electrons, who's losing electrons. If you lose an electron, Leo, loss of electrons means I'm oxidized. If you gain an electron, gain of electrons means I'm being reduced. So we go through prioritization. In this case would go to the fact that this has to, in CH4, has to add up to 0. Hydrogen would be +1, group 1. So therefore carbon must be -4. Oxygen by itself would be 0. Now on the product side, prioritization goes to that the sum has to equal up to 0. Oxygen is -2, and therefore carbon is +4. And then over in H2O, again, prioritization goes to hydrogen has to be +1. The sum has to equal to 0. So this means this has to be -2. After you've assigned all the oxidation states, you then want to look for who is gained, who is lost. So we can see carbon went from -4 up to +4. So that means it had to kick out some electrons. So therefore carbon is being oxidized. Okay, if the number is getting more positive, that means it's being oxidized. Hydrogen went from +1 to +1, so nothing changed there. But oxygen went from 0 to -2. And how did it become -2? Well, those same electrons that carbon kicked out, oxygen gained, and it then subsequently got reduced. Okay. Now, one other thing that we can declare when we're doing these redox reactions is defining what's called our reducing agent and the oxidizing agent. And so in these chemical reactions, you have this oxidation and reduction that's happening simultaneously. Someone's losing an electron, someone's gaining those electrons. And so we can declare the reducing agent as the reactant, the total reactant, that allowed the other element to become reduced. So because I gained your electrons, I allowed you to become reduced. I'm working for you. I'm your agent. So I'm considered to be the reducing agent. Whereas the reactant that allowed the other element to get oxidized is considered to be the oxidizing agent. Because I lost my electron, I allowed you to become oxidized. And so to identify your oxidizing and reducing agent, you want to first assign your oxidation states, figure out who's being oxidized and reduced, and then from there you can look at the reactants and state who the reducing agent is, who the oxidizing agent is. Okay, so in this example, we would say that sodium has a 0 charge, chlorine also 0, elements by itself, and then as they form this compound, sodium becomes +1, chlorine becomes -1. So sodium, we could say, has lost electrons, so it became oxidized. And then we would say chlorine has gained electrons, so it is reduced. Now, when we go to assign the agent, we now are going to pick the reactant, the total reactant that allowed the other element to do that thing. So because chlorine allowed sodium to become oxidized, chlorine is considered to be the oxidizing agent. And because because sodium allowed chlorine to be reduced, sodium is your reducing agent. Okay. So assign your charges, figure out who's being oxidized and reduced, and then assign the agents accordingly. Now let's look at this final set of problems. We have FeMnO plus MnO4 permanganate plus 4H plus, and that's producing iron 3 plus MnO2 plus H2O. So we go through and assign all of them their oxidation states. So we would put 0 here, and then we know that the sum of the charges have to add up to -1. And so oxygen takes priority as -2. If that's -2, but there's 4 of them and it has to add up to -1, our unknown manganese has to end up being +7. Hydrogen would be +1. Iron would be 3 plus. Now on the product side, we know that the sum here has to add up to 0. Oxygen takes priority as -2. And so to figure out what the manganese would be in this case, our unknown would equal +4. And then in water's case, they have to add up to 0. Hydrogen takes the priority of +1, but there's 2 of them. So oxygen would end up being -2. We then go through and look to see who's being oxidized, who's being reduced. Iron, we see went from 0 to +3. And so this would be considered oxidized. And we also noticed that manganese went from +7 to +4. So the number went down. It's being reduced. It gained some electrons. Okay, so now that we've identified who's been oxidized, who's been reduced, we can now figure out which reactant would represent our oxidizing agent and the reducing agent. All right, and so if we look at MnO4 minus or permanganate, well, permanganate allowed iron to be oxidized. All right, and so we're going to label this as the oxidizing agent. And then similarly, iron allowed manganese to become reduced. And so iron works as the reducing agent. Make sure when you're assigning the agent, you always declare the entire reactant that allowed that to happen. It'll be opposite to whatever you've assigned as being oxidized and reduced. But again, the entire reactant. Okay. 2 quick examples here. For the first reaction, we have +4 here and 0. +2 and +2 as their oxidation states. We see that SN is being reduced. It's going down. It's gaining electrons. Calcium is going up. It's losing electrons. It's being oxidized. So therefore, we would say that SN4 plus is working for calcium. So it's the oxidizing agent. And calcium is working for SN4, and so that is your reducing agent. And then final example here, we have F2 and sulfur. So F2 by itself, pure element would be 0. Sulfur by itself, pure element would be 0. This looks like it's not a balanced equation, so we'd want a 2 here. Sorry, a 2 here. And that'll balance it out. And so we would end up with here seeing -1 and +4. And so we would say that that fluorine is being reduced because the number is going down, it's gaining electrons, and sulfur is being oxidized, it's losing electrons. And then our oxidizing agent is going to be fluorine. And our reducing agent is sulfur. Remember, it's allowing the fluorine to become reduced. It's working for it. I hope this video helped you understand oxidizing agents, redox reactions, and how to predict them. Make sure you guys like, comment, and subscribe, and come back to see more videos. I'll see you guys in the next video. Have a great day. Bye-bye.